YouTube is live.
Do it live. Behind the scenes footage of erasing all the boards.
All right, and you are live on.
Hooray!
All right, I'll monitor.
Okay. Turn on the game if you need to. All right, welcome to Math Thursday, everybody. Just erasing the boards from last week. Always exciting time. All right, so let's start off with a little quadratic. Let's do x squared plus 6x yeah. Okay. Ooh, Vine, can you algebra? What do you have a test over? Let me know a little more detail about what you have a test over, and we can get you going on that. Or I should say, we should be able to get you going on that. All right, guys, welcome to Math Thursday, where we get into any math questions that you have, any content, any specific questions you need help on. If you have a math test coming up or a quiz, or you're just interested in something, maybe you saw something online and you weren't sure how it worked out, let me know. Pop it in the chat. So typically we spend most of our time talking about pre-algebra through like algebra 2, a little bit into pre-calc. But anything, if you have like a question about pre-calc or calculus or anything beyond that, go ahead and put it in the chat, because we have a great community and we can get you an answer. So in the meantime, everybody loves quadratics. Let's solve it. Sorry, I had some really bad allergies this week. So Elizabeth, subtracting the 40 can be one way to start it. Yeah. You can subtract the 40 and then you can factor it to solve it. Yep, that's one way. You could also complete the square on this one. Okay. Zakino, yes, I teach high school primarily, like 10th grade and 11th grade. Okay, so we've got 4. Okay, so Francis, that is one answer. But there's actually a another answer that could work for this too. Let's see. Did you ever create lit term for ELA? Nope. That's okay, Zach. You know, if you have questions about 8th grade, I taught middle school math for a really long time. So our whole goal here is to really talk about like pre-algebra through algebra 2 into some pre-calc stuff. So stick around, because you'll see that we'll do some things that are more like middle school level, like 7th and 8th grade. But we also do a lot of high school stuff too. So this is usually something that that you will see primarily in algebra 2, but you might see it in algebra 1. So next year in 9th grade, you'll probably see it. So Big Monkey, we do not get into Calc AB, but if there's something specific that you have, put it in the chat and somebody might be able to help you out. Oh, I just realized I can't see my YouTube chat. Hold on, guys. There we go. Okay. Okay. All right, so here we go. So when we're looking at this, there are a lot of different ways to solve this. So this is what's called a quadratic. And the reason it's the way we know that it's a quadratic is because of this little exponent here, right? So x squared, that means it's a quadratic. So there's mainly two ways that you could go about solving this. So Matthew is asking, why wouldn't you add the two variables? So I wouldn't add the two variables together because this is x and this is x squared. So I can't combine them because they're not what we call or like terms, okay? So what I have to do is, so I'm gonna go ahead and I'm just gonna solve this by factoring, okay? So to solve by factoring, I'm going to subtract 40 from both sides. Because when you're solving by factoring, you want it to be equal to 0. Okay, so now what I'm going to look at are, thank you, Erin. I'm going to look at what multiplies to make negative 40 and adds to make positive 6. So most of you were able to see that. Ooh, Alden, yes, I do trig. I love trig. But the two numbers that multiply to negative 40 and add to 6, to positive 6, would be positive 10 and negative 4. Okay, so right there, once I figure out these numbers, this actually becomes my binomials. Equals 0. So now what I've got, the reason I can do this to solve this is because now I've got two things that are being multiplied together to equal 0, right? So if I just had like a times b equals 0, I know either a is 0, so it equals 0, or b would be 0 to equal 0. So either if x plus 10 equals 0, the whole thing's going to equal 0. Or if x minus 4 equals 0, the whole thing will be 0. So x is going to equal either negative 10, I don't really know where to write this. I'm going to put this back up here just so it's all on one spot. So either x equals negative 10 or x equals positive 4. Okay, so you might have been able to find that x was positive 4 just kind of by guess and check, right? 4 squared is 16, plus 6 times 4 is 24. 16 plus 24 is 40. But negative 10 squared is 100, okay? And 6 times negative 10 is negative 60. So 100 minus 60 is also 40. Okay, so with the quadratic there, you can find that oftentimes there are different, excuse me, oftentimes you will have more than one solution to a quadratic equation. Not always, right? They're not always going to be more than one solution. There's not always going to be two solutions, but quite often there are two solutions. Okay. All right. Okay, so medium to difficult compound inequalities. Okay. So yeah, guys, so put if there's anything specific you want me to go over, just put it in the chat, and I will do my best. But as you can see, it kind of keeps filling up and filling up and filling up. So I saw synthetic division of polynomials, and we can do long division too. So I'll put division of polynomials on here. What was it that I just said? Tiba, I do geometry, yes. What was it that I just said? Pinkie Pie, what do you mean help on coordinates? Oh, compound inequalities, that's what it was. Okay. All right. So guys, let me jump ahead. Let me answer Pinkie Pie's question about coordinates. So coordinates, I'm just going to kind of go through the basic things. So when we've got these, our coordinate plane, right? This is our X axis, and this is our y-axis. Okay, so going all the way through, right? It's really just, these are just two number lines. Okay, so it's two number lines that are lined up. They cross at a 90-degree angle. Okay, the reason we have two number lines is because we're talking about the relationship between two values or two variables. When x is one thing, y is the other thing. Okay, when x is 2, y is 3. Okay, so I find where when x is 2, y is 3. So that means that when x is 2, that's where x would be 2. And then y is 3 here. And I plot them right here where they meet up. Okay, so that point right there is where x is 2 and y is 3. So these are all positive x's. These are all negative x's. These are all positive y values. These are all negative y values. Okay. All right. So if I had like a negative number, right? So let's say when x is -4, y is also -4. Let's do that. Okay. So I find where x is -4 is right there. So I'm just counting out, right? This is 0. So I go 1, 2, 3, 4. And then where y is -4, I go 1, 2, 3, 4. And where they meet, that is that point. Okay. So that's the basics of the coordinate plane, okay, of just the coordinates. So the big thing is to remember x comma y. It's always the x value first. So you walk out to the x value, and then you can take the elevator up or down to the y. Okay, but always start back here at the origin where it's 0, 0. Okay, and you'll be fine. Okay, so compound inequalities. Yep, rise over run. Yep. Quadratic lines of regressions. Okay, we've got long division. Okay, so triangle proof. So guys, the questions with proofs right now, we've got a lot of stuff going on in the chat, sorry. With the proofs are really hard for me to show in this particular like venue. They're really hard for me to show because there's so much writing and it would be kind of hard to see. But if you need specific explanations of like different postulates or theorems or something like that, that you can put into the chat and I may be able to get into it. Like Not Ashley is asking for angle theorems. Do you mean like the angle bisector theorem? Do you mean like triangle congruence? What do you mean? I'm not really sure about any specifics. Eddie, I've got division of polynomials. Anything else that you want to do? Okay, angle bisectors. All right, so I'll get to angle bisectors in just a few minutes. You're third on the list. Okay, compound inequalities. So an inequality is if you've got something like x is less than or equal to 3. Okay, so this one, pretty straightforward, right? These are like the first inequalities that you really learn. When you first start talking about variables, you sometimes get into a little bit more of, the inequality piece when you start learning about variables and stuff like that. So x is less than or equal to 3. So if we look at this on a number line, so let's see if this is 0, 1, 2, 3, -1, -2. So if I'm plotting this on a number line, x is less than or equal to 3. So at 3, I'm going to fill in, I'm going to put a solid circle there, okay, a solid dot there, because it can be equal to 3. If it were not able to be equal to 3, it would be an open circle like that. Okay, so if it were just x is less than 3, so that means it's not including 3, then I would leave it open. But I'm going to have a closed circle there. And then what I would do is I would color in all the rest of the number line where that x value could be. Okay, so x is less than or equal to all of those 3, or less than or equal to 3. Now, what makes it a compound inequality is that it's not just this, okay? It's x is less than or equal to 3, but then usually there's another boundary. Okay, there's another boundary where maybe it can be less than or equal to 3, but it has to be greater than 0. Ugh. So now anything below 0 is not acceptable. Okay, it has to be a positive. Basically, this is saying it's got to be a positive number that's less than or equal to 3. So now this is going to change up our graph a little bit, right? So I'm going to redraw this number line. Okay, because now at 0, I've actually got a lower limit. Okay, so now, here we go. We're at 0 and it's an open circle because it can't be equal to 0. So 0, so it's greater than 0 and less than or equal to 3. Okay, so this is what we call an and inequality because it's greater than 0 and less than or equal to 3. Okay. The other type of compound inequality that you could have would be like, well, actually, hold on. So we can have and where they're sort of overlapping. We can have or where they're opposite directions. So if I wanted x to be less than or equal to -5, or x is greater than 4. Okay. So a lot of times, teachers, myself included, when you have like the number line, when you're drawing it, you really just have to do like -5 and +4. You really just have to mark those two. Because all we really care about is, oh, this is kind of hard to read, isn't it? All we really care about is, do you understand that if they're overlapping or opposite directions? But we can do this. 3, 2, 1, 0, 1, 2, 3, whoops, 4, 5. I'll make that -5. 4, 3, 2, 1, 0, -1, 2, 3, 4, 5, -5. Okay. All right. So now it can be equal to -5. So I do a solid circle there. And I'm going to fill in that way because it can be less than or equal to -5. Okay. And then 4, it's got to be greater than 4. So it's going this way. Okay. So it can be greater than 4 or less than or equal to -5, but it can't be anything in between. Okay. All right. Ryoman transversals. I'll write that down. I see differentiation, implicit differentiation. I'm not really sure how we would be able to do that here. But all right, so Felicity, you've been asking for long division. Okay, so I'm gonna do that actually because we are leading into division of polynomials right now. Okay. So with division of polynomials, so polynomials are many-termed equations. Or not even equations, expressions, okay? When we're talking about polynomial functions and things like that, we're gonna get into graphing them, and there's all these terms, and like it's crossing the x-axis and it's crossing the y-axis and all of that kind of stuff, okay? Hold on, guys. Okay, I want to just make sure that I start with some polynomial things that'll actually work. Okay. All right. So with dividing polynomials, you have to go through long division. Okay. All right. So long division, we're just going to go with the basic algorithm. Right? So the basic algorithm is where we've got, I don't know. So we have, let's do 4,640. I just want to make sure we don't have any remainders or anything. Divided by 32. Okay. So 4,640 divided by 32. Now, I know what everybody's saying. You just use a calculator. I just used a calculator to double check this. Yes. However, you'll see why it's important to understand what's going on here. Okay? Because when we get into division of polynomials, sometimes I have to teach my high school students how to do basic long division because they never learned how to do it. They did the repeated subtraction, which works great for numbers. It works great. It is awesome when you're first learning it. But the way that you do this is actually kind of setting the groundwork for long division of polynomials too. Okay, so 4640 goes inside the little house. 4640. And 32 goes on the outside. Okay. So now what we're looking at is we're just going to focus on this 32, and we're only going to focus on a few pieces at a time. I'm going to use this. Okay. All right, so 32 can't go into 4. Nope, so we've got to add another digit. 32 can go into 46. 32 can go into 46 one time. Now, so I put my number up here, I do 1 times 32, and I put that down here. And then I subtract. So 46 minus 32 is 14. Okay, now my next number, I bring down my next number, which is 4. Okay, kind of got erased, but it's a 4. So 144. So I'm going to say, let's see. So this is 30. This is 140. I'm going to try 4 times because 30 times 4 would be 120. So let's see if that's enough. So 4. So 4 times 32, that's going to be 8 and 12. Great. Okay. So now I'm going to subtract again. So 4, let's see. I'm going to do this. I'm going to borrow a 3. 14, that's 6. And that's 1. Okay, great. Now, if this number had been greater than this one, that would have been a problem, right? Okay, and now I'm going to bring down my last number, which is a 0. So 160. Now, looking at this, I see that this ends in a 2. This ends in a 0, and I know that 5 times 2 is 10. So I'm going to try 5. So when I look at this, I do 5 times 32 does give me 160. So that's going to be no remainder. Okay, I kind of ran out of room here. Okay, so 4640 divided by 32 equals 145. Now, again, those of you who are like, ooh, it's supposed to be a high school math class. Ooh. It is, because now we're going to do it with polynomials. Okay, but the basic idea with long division is you're looking at this term like one at a time, and you're doing this times this down here, subtract, bring it down. This times this equals this, subtract, bring it down. Okay, it is the same exact process for long division of polynomials. Okay, all right. So let's do a polynomial division. Okay, let's start off pretty easy. 6x squared plus 7x minus 20 divided by 2x plus 5. Now, I like to show this with my students when we are, when we're working with polynomials and trying to kind of see when you have a polynomial that, all right, good job, Felicity. When you're trying to see like where the roots are and things like that, this does become much more useful. Okay, I'm going to set this up in the exact same way. Okay, so this is going to go inside the house. This is going to go outside the house. Okay, Romans, this is high school. This is usually something that you see in Algebra 2, maybe definitely pre-calc, but Algebra 2 is usually a pretty polynomial heavy course. Okay, and then 2x plus 5 is out here. All right, so I'm going to go back to just looking at that one term. Now here, I do have two terms here. Okay, I have 2x plus 5. Okay. I'm only going to pay attention to this 2x. I'm only going to look at this 2x and this 6x squared. I'm going to think, okay, what times 2x is going to give me 6x squared? Okay, this plus 5 is just going to go along for the ride. Okay, so 3x, right? So 3x, now I'm going to line up my 3x here. I'm just going to put it over this 7x, okay? Just to keep it a little bit organized. But I'm going to do 3x times 2x is 6x squared. 3x times 5 is 15x. I subtract. Those cancel out. If these don't cancel out, go back. You did something wrong. Okay, they have to cancel out. 7x minus 15x is negative 8x. And now what do? We bring the next one down. And that's minus 20. Now again, I'm looking at 2x. I'm just looking at the first two terms. What times 2x equals negative 8x? Okay, what times 2x gives me negative 8x? Negative 4, good. So negative 4. So negative 4 times 2x is negative 8x. Good. Negative 4 times 5 is negative 20. Woohoo! When I subtract these, they cancel out and I'm left with no remainder. Okay, so 6x squared plus 7x minus 20 divided by 2x plus 5 is 3x minus 4. Okay, this is another way, if you know one of the factors, you can figure out the other factor. Okay. Okay. Well, lead off grand slam. Obviously, we didn't leave long division in 4th grade, right? Just here we are doing it here, and you don't always have Desmos to tell you what to do, right? Now, there is a really nice way to divide, which is called synthetic division. So synthetic division is where you're really just paying attention to the coefficients, right? So synthetic division is really helpful for, but look, like when you look at this and compare it to that long division that you did in 3rd and 4th grade, like, come on, it's the exact same idea, right? Okay, so this is just long division right here. So synthetic division is a big time time saver. It is really a shortcut, but it can be very useful for, I mean, because long division is long division, right? It's long division. It takes a long time. Synthetic division is quite a bit more efficient. But I often will, with my students, I'll at least show them and ask them to learn long division. I always like to have students learn the long way of doing things before I show them the shortcut. Because otherwise they don't know, if they don't know what the shortcut is, if they don't know where the shortcut is coming from or what it's helping to bypass, they're not going to appreciate the shortcut, right? And everybody's always looking for more of a shortcut, and, you know, using the operations on the calculator, like that's the shortcut. Sorry. Okay, so synthetic division is kind of a shortcut, okay? All right, so what we're going to do is we are going to look at this. Now, this really works well if this is, if this just has a coefficient of 1, okay? All right, so let's see. You could definitely, lead off grand slam, you could definitely put the x minus 3 at the top, or on the, like, in the denominator and cancel out, absolutely. But if you're not really sure how to factor this, this is basically what it's doing, right? It's kind of like you know one factor, so you're trying to figure out the other factor. That's what division is you know one thing that's going to multiply together, okay? And so you're trying to figure out the other one, right? Okay. Let's see. Okay. So what we're going to do is we're going to make a little, it's almost like a little upside down house. Okay. And what we're going to do is we're going to put 3 out here. Now, the reason we're putting 3 out here is because it is the opposite of this. Okay, so this is -3, so this is going to be +3. And then I'm going to line up all of my coefficients from this other side. Because really all I care about are the coefficients. That's what I'm really looking for when I'm dividing. So this is a 1, this is a -2, this is a -5, and this is a 6. Okay. All right, so first step, bring this 1 down. There's my 1. I'm going to do this times this and bring it here. Okay, so 3 times 1 is 3. Add. -2 plus 3 is 1. 3 times 1 is 3. Add. -5 plus 3 is -2. 3 times -2 is -6. Add. 0. This last term is always going to be your remainder, and you kind of always hope that it's a remainder of 0, but if it's not, that's okay. Okay. So now what this has given me is this has given me my coefficient of my answer, what's divided. Okay. Your answer is always going to be 1 less degree than what you started with. Okay, so here I started with x to the 3rd. So this is going to be x squared. So this is +1x and then -2. So my solution to this is x squared plus x minus 2. Okay. Now from that, I could, factor this, right? Or I could keep going to solve this. So this is when you've got like kind of a crazy curve, like this polynomial function, and you're trying to figure out how many different times it crosses and where it crosses the x-axis and all of that. This can help you get there. Okay. So then you could take this and you could factor this to be x plus 2 and x minus 1, right? So you could take this whole thing, this x cubed minus 2x squared minus 5x plus 6 is x plus 2 times x minus 1 times x minus 3. That's what you could do, okay? All right. Okay, so I know there's a lot of, stuff. What do you do with the other x from x minus 3? Oh, with this x, so you're really just paying attention to the numbers. So if you were trying to fully factor this polynomial, x cubed minus 2x squared minus 5x plus 6 is the same thing as x minus 3 times x plus 2 times x minus 1. Okay? How do you know if you add or subtract? Do you mean here, Hudson? So this way is always adding. Synthetic division is always adding. Now, when you're doing long division, you're subtracting, okay? But here you're adding those coefficients as they're going down, okay? So it's a little bit weird, but it's a different process. What I like is that they look so different from each other that you can kind of remember, yeah. Oh, so the factors of x plus 2 and x minus 1, I just looked here and I saw that something that are two numbers that multiply to -2 and add to +1 are +2 and -1. Okay. All right. Dylan, simplifying radicals. Okay, I've got compound inequalities done, division of polynomials done. Okay, angle bisectors and simplifying radicals. Okay, I'm actually going to do simplifying radicals first because it works a little bit more, it works a little better with these quadratics. Okay, so one thing, so let's look at the quadratic. Let's look at one. Let's look at one that is, okay. So let's do x squared plus, actually I'm going to do plus 8x. So we're going to do kind of a detour off to, hold on, let me think about this. I want to do, not that, let's do 48. So that's going to be, yes, 32. Okay. So looking at this quadratic. Okay. So here, I know we already solved a quadratic tonight by factoring, right? This one I'm going to do a little bit differently. Oh, shoot. Is this one factored? 16. That's 48. No. Minus 32. This one would be factorable, wouldn't it? My mind is not working well right now. No. Yes? No. No, it's not factorable. Oh my God. Oh, you guys saw the spinning wheels there. Okay. Holy moly. Okay. All right. So I'm going to do something called completing the square. Okay. So I'm not going to square root it, but I'm going to do completing the square. So completing the square means if this coefficient is 1 and this is an even number, I can actually force it to be a perfect square trinomial. Okay, so perfect square trinomials are things like x plus 2 squared, x plus 3 squared. Okay, now when I square these, so x plus 2 squared is going to give me x squared plus 4x plus 4. X plus 3 squared is going to give me x squared plus 6x plus 9. Okay, so in this case, what I'm going to do is half of this 8 is 4. So I can actually write this. This could be, if this is x squared plus 8x, if this were x squared plus 8x plus 16, that would be a perfect square. That would be x plus 4 squared. Okay, now if that's a perfect square, I can take the square root of both sides. Okay, so Dylan, I am going to get to simplifying radicals. Yep. Okay. But I can't just add in 16 to an equation willy-nilly, right? What I do on one side, I have to do on the other. So if I need to add 16 on this side to make it a perfect square, I need to add 16 on this side to also make it a perfect square. So that's going to be 48. Okay, and now I can take the square root of both sides. The square root of something squared is just that something, which is x plus 4. Now over here, I've got the square root of 48. Square root of 48, it is not a perfect square, okay? But I can simplify it. So this is where we get into simplifying radicals. When I'm simplifying a radical, what I want to look for is it divisible by perfect squares? Does it have perfect square factors? So my perfect squares are, 1, yes. I could do 4. See, that's 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and we're beyond 48, right? So looking here, I can say 4, yes, it is divisible by 4, right? But let's see if we can go higher. If it's divisible by 4, I'm going to check to see if it's divisible by 16. 48 is divisible by 16. Okay, so I'm going to rewrite 48 as a product of a perfect square and whatever's left over. So 16 times 3. Okay, so 16 times 3 is 48. Now I can take the square root of 16, right? That is 4. I can't take the square root of 3. Okay, so what I'm going to do is I'm going to take the square root of 16, which is 4, but I can't take the square root of 3, so that's going to stay as square root of 3. Okay, so now I've got this radical. So now I've got this here. I've got x plus 4 equals 4 square root 3. Okay, it's my simplified radical. Now I'm going to subtract 4. Needs to be plus or minus, right? Subtract 4. X equals negative 4 plus or minus root 3. And that is your solution. The reason it's plus or minus is because technically the square root of 48 could be the negative version of square root of 48, or it could be the positive version of square root of 48. Okay, so it could be positive 4 root 3, or it could be negative 4 root 3. So that's why you have the positive and the negative. Okay. All right. Vice. Ooh, the ASVAB. Okay. So I do teach, there's a lot of, what happened to the 4 next to the square root 3? Oh, you're right. I'm sorry, I left the 4 off. Thank you. Negative 4 plus or minus 4 square root 3. Thank you. I dropped the 4. I didn't mean to drop the 4. I'm sorry. Okay, it's negative 4 plus or minus 4 root 3, but I can see how that would be very confusing. Okay, sorry about that. Let's see. Okay, so chain rule, we're not going to get into the chain rule. We tend to stick with just like pre-algebra through algebra 2 and some pre-calc, and that's getting into a bit more of calculus things. Let's see. Derek, you want to do adding and subtracting positive and negative numbers. Okay, I think we were going to talk about angle bisectors a little bit. Okay. So an angle bisector, and that'll also get us into a little bit of transversals. So an angle bisector, when you have an angle, and you have a line that cuts that angle exactly in half. Okay. So we're going to do D, E, F, C. Okay. So I'm going to tell you that ray CE bisects angle DCF. Okay, so there's a lot of geometry stuff going on here. So ray CE, which a ray is part of a line, basically. It starts with a point and it extends indefinitely in one direction. Okay, so these are all three rays. So we've got ray CD, ray CE, ray CF. Okay, now we have angle DCF. So whenever we're looking at an angle and naming an angle, I can't just say angle C for this because there's actually a lot of different angles that are at C. But whatever's in the middle is the vertex. That's what we call kind of like the corner, and where the angle really is C. Okay, or is the vertex in the middle. So DCF is the angle that starts at D, goes through C, and ends at F. So I'm talking about this whole angle here is DCF, right there. And CE bisects it. Bisecting means that it's cutting it exactly in half. Okay? So I've got this half, and they are congruent. Okay? So if you were writing a proof for this, I know it's really hard for me to show you how to like fully write a proof, but one of the first things that you would need to establish is just because it says it bisects it, that means that angle DCE is congruent to angle FCE. Okay, that's the first thing that you would want to establish. Oh man, Shiloh, factoring polynomials. I just did a whole bunch on factoring polynomials and factoring quadratics. Go over to YouTube so you can rewind it and you can watch it there, okay? All right, so another neat thing about angle bisectors is that, I'm actually gonna move this point D out a little bit. I'm gonna move it out to here. I'm not gonna change much of anything except move it there. Okay. All right. So angle bisectors right here. So we've got the angle gets cut in half, exactly in half. Okay, now another cool thing about angle bisectors is that what this means is that as long as this is a right angle, and this is not that one, and this is a right angle. I tried to get them as close as I could. Okay, they are perpendicular. Okay, and what that means is that this segment and this segment are also congruent. Okay, and what that also means is that this segment and this segment are congruent. Okay, so when we talk about an angle bisector, I talk about how you've got these loaded terms, right? So these loaded terms are where just saying that that's a bisector means all of this other stuff that's in red is true, just from me telling you that that's an angle bisector. All of everything else is true. Woof. Okay, so trisecting, somebody's asking about trisecting, that would mean where you're dividing it into 3 equal things. Okay, same idea. Okay. Yep, so Casey, I'm going to get into transversals in just a second. All right, so that's angle bisectors. Oh, we're doing a lot of geometry tonight. That's exciting. I feel like everybody in their geometry class right now is getting into proofs, and it is a rough world out there for proofs. Yikes. Okay, transversals. Transversals are, we got parallel lines. Those are pretty parallel. Okay, but you know what's going to make them actually parallel? It's because I say they're parallel. There we go. I marked them. They're parallel. Okay. And then we can have another line that's called a transversal. Okay. This line is not parallel, obviously. Okay. But it is called a transversal because it crosses 2 or more lines. Now, what it does with this is that since these lines are parallel, that top line, that intersection, is exactly the same as that intersection. Okay, so they're exactly the same, which means that all of their angles are exactly the same. Okay, now they're not all congruent, right? But they're the same like arrangement. So this angle that's up here is the same as this angle up here. Those are called corresponding angles because they're in the same location. So this one and this one, this one and this one, this one and this one. Okay. Now, this angle is also going to be that same measurement because they're vertical angles and because these are corresponding angles. Over here, this one here is going to be the same as this because they're corresponding. And that's going to be the same as that because they're vertical. And that's going to be the same as that because they're corresponding. Okay, so really, it's exactly the same arrangement for each of these intersections. Okay. We've got linear pairs, we've got supplementary. Now, ultimately, there are only two options when you're solving these transversals, right? Even if you've got like, if you're just given a couple of angle measurements, or if you're given like an algebraic expression for one of them, like the only two options for any of these angles in the relationship are they are either congruent or supplementary. That's it. That's it. Any pair of angles here, they are either congruent or supplementary. Again, that's it. Okay, so you have to ask yourself, are they congruent or are they going to add up to 180? Okay, so can you add a second transversal that intersects to the first one? Do you mean something like, usually that's kind of something like this, right? And then, so then again, same things don't really, it's all still the same, right? Okay, so alternate exterior would be these two angles out here. Alternate means they're on either side of the transversal, related to this one here, right? These would be alternate, either side of the transversal, and they're exterior because they're outside of the parallel lines. Alternate interior would be like these two. They're still on the opposite sides of the transversal, but they're inside the parallel lines, and they are congruent. Same side or consecutive interior would be these two right here. Okay, because they're on the same side of the transversal and they're both inside the parallel lines. Those are supplementary. Okay, when you look at these diagrams, they may not be drawn exactly to scale. However, you do have, they're going to be drawn in a way that you can tell one's acute and one's obtuse. Okay, so you'll be able to tell, like, is this the big angle or the little angle? Again, is it congruent or is it supplementary? Those are the only two options. Okay. All right. Okay, so Elian, I can't really read the name. Unit circle. Yeah, magic. I'll talk about the unit circle in just a minute. So Elian, with the proofs, proofs are really hard for me to show in this context because just kind of all the writing and things like that. But that's what I was talking about here with this, was if you are given this information, all of this stuff in red is true. So if you're writing it out in a proof, you're going to need to establish all of these things are true. So that's just kind of one of those things with writing proofs. Okay, so magic, unit circle. So unit circle, there's a lot of, what I always recommend to my students is with the unit circle, spend a fair amount of time when you first get it, just looking at it. Like, just look at the unit circle and see what patterns you can pick up on. There are ways to remember it. I know there's like a hand trick that you can do. I never remember it. But if you just look up hand trick unit circle, okay, it's basically like this is 0 and this is 90. And you do 30, 45, and 60. And it's like whatever's on the top and whatever's on the bottom. So on the top is always going to be the root. And on the bottom, it's going to be like 2. So if you're doing like 30 degrees, right? So that means that it's root 3 over 2 for like cosine and sine, or cosine and sine, right? So it's something like that. I don't remember the exact kind of thing, right? Yeah, so it's the angle measurements are pretty easy to remember, but it's there's something with the unit circle and the hand trick, right? So it's like the little hand trick to remember that, right? So you've got like, you know, root 2 over 2 or 2 over root 3, you know, that kind of thing. Well, you wouldn't do root 3 on the bottom, but that's one thing that I know is really handy. But yeah, the unit circle, once you know quadrant 1, that's the other piece. That's the biggest thing, is you only have to learn quadrant 1. Because once you learn quadrant 1, the rest of the quadrants are still following the same pattern with the 30, 45, 60. But it's just a question of the symbols, right? And then you can get into that all students take calculus, right? That whole thing with like which ones are positive, which ones are negative. But if you just use the hand trick for remembering the coordinates, okay, that can be really helpful. And then just look for the, yeah, so we're root 3 over 2 and 1/2 for 30. Yeah. Yeah. So when you're looking at that, then you can go through, and do like, is it positive? Is it negative? That kind of thing. Okay. So yeah, the hand trick is really cool. This is for the unit circle. So the hand trick, you kind of figure out like, it's the 0 and the 90, and then it's like for however many angles there are, you can kind of remember it that way, right? It'd be funny to get that tattooed on your fingers. Okay, let's see. Okay, we got everything there. Let me see, hold on. Symmetric functions, algebraic. All right, so Andrew, do you have a specific one that you're looking at? Yeah, so magic, from the first quadrant, they'll all be, it's the same pattern. It's all just a pattern that it goes through. Then it's just, they're not going to be changed. The only thing that really changes is the symbols, or not the symbols, but the signs, right? Just, you know, in quadrant 2, it's going to be X is negative, Y is positive. In quadrant 3, it's going to be X is negative, Y is negative, right? Oh, I love piecewise functions, Caitlin. Oh, okay. So, all right. So when you're looking at the even, odd, and neither, so I can do this really quick. So an even function. Oh, Pewpop, why you don't think high schools should teach proofs? So here's the thing with proofs is I'm not saying that you shouldn't have to support your answers and support your reasoning with justifications and statements. I'm saying that writing out a 2-column proof for a really complicated geometric diagram is not the best use of your time in a high school geometry class. I think I show my students what 2-column proofs look like. We might do 1 or 2, but what I'm more interested in is, can they explain it to their neighbor? Can they explain how they got their answer to me? Can they justify it? Writing paragraph proofs, I think, is more beneficial, being able to justify their thinking and justify their reasoning. But writing a formal 2-column proof, I don't think it's really worth it. I mean, that's just kind of my opinion, right? But as when I've been as a high school math teacher for so long, like, I think the logical reasoning is important, but the actual like nitty gritty of like specifically writing out a proof, not worth it. Not worth it. That's just, there are much better things to do. Like, let's get really good at graphing lines. Like, that's the stuff that you need to be able to do, really. For moving on. If you become a math major, you're going to take entire courses on writing proofs. That's the place for it. Okay. All right. So even, odd, and neither functions. So even functions. So if you do f of negative x, it's going to equal f of x. That's going to be even. Okay. So it's not really going to necessarily change what it is. Okay. So an odd function is going to be, if you have f of negative x, it's going to be negative f of x. Ugh, I hate this. I just hate memorizing like little tricks and things like that. So if f of negative x doesn't equal negative f of x, it's neither. It's neither even nor odd. Okay, that usually means that it's just not a function. For the evens and the odds, what you're really looking at is, and that's just like, you're looking at the degrees, you're looking at the shape of the graph and things like that. I don't love this. It's a little more interesting, a little more fun when you can actually like graph them and move them around and things like that. But just kind of basically going off of the function itself is a little bit, okay. All right, guys, it has been a full hour. Connor, really quick, I can do SAS, ASA, AAS. So SAS is side, angle, side. ASA is angle, side, angle, and angle, angle, side. That is where you're looking at if two triangles are congruent or not. So if you have two triangles, okay, this is usually based on proofs also. And I tell you that these two sides are congruent and these two sides are congruent. And this angle is congruent, okay? Those two triangles are congruent because there's only one way that you can connect these two side lengths together when they're locked into that angle. So this is side, angle, side. So if you're writing a proof, if you establish that this side is congruent and this side is congruent, and this angle is congruent, the included angle, so the sides make the included angle. If you can prove all of that, you've proven that those two triangles are congruent, SAS theorem. Okay. All right. So then if I tell you that so that angle and that side are congruent, and this angle are congruent, then there you've got an angle, a side, and an angle. And if all of those are congruent, the two triangles are congruent because, again, there's only one length that's going to fit and join in exactly one spot for these two angles that are locked in. Okay, so that's ASA, and so that's angle, side, angle, and side, angle, side was the one that we did before. Okay, guys, I can feel my voice going, and I've still got to teach tomorrow morning. So I need to get going. But Excellent job this week. I'm proud of everybody who did really well on their tests and quizzes and all of that good stuff. And I will see you next week for another Math Thursday. Bye. Oh, that's the wrong mouse. Okay.